The large blade that is fixed in a horizontal position above the fuselage is the main rotor. This main rotor makes multi-directional movement of the helicopter possible. One might safely say that this is the single most important feature of helicopters. The main rotors are called blades. These blades are linked to the rotating motor mast through the central rotor hub. Known as the swash plate. The swash plate is connected to the blades by means of control rods and transfers corrective, cyclic, and other lever actions to the blades. The small rotating blade fitted directly below this is the tail rotor. This tail rotor counteracts the torque forces generated when the main rotor turns. It has the important function of preventing any needless rotation of the fuselage. Also, when hovering, it acts to control the aircraft fuselage. To get lift, unlike fixed-wing aircraft that run along the ground, a helicopter, which can convert the engine output directly into lifting force, does not need wheels to run along the ground. For that reason, many helicopters are heavy, and in place of wheels that are restricted in terms of takeoff and landing, they have a robust framework for landing on called skids. They are special devices that fixed-wing aircraft do not have. As opposed to fixed-wing craft, which as a rule only move forward, the helicopter can fly freely in multiple directions. There are large windows ensuring that the pilot has a wide field of vision. The windows situated around the legs of the craft permit visibility directly downwards and are there because of the helicopter's multidirectional travel. The following are the three key devices used for maneuvering the helicopter freely. The lever in front of the seat, in the center, is the cyclic lever. The helicopter posture is controlled with this. The lever beside the seat is the corrective lever. This controls the helicopter lift. The pedal fitted on the floor is the anti-torque pedal. This controls helicopter direction. Use the corrective lever to make the aircraft rise. The corrective lever and blades are linked, so if you raise or lower the corrective lever, the blade angles change. When the rotor rotates, an airflow is generated by each blade. If you raise the corrective lever, the speed of the vertical airflow from the blades changes. If the speed of airflow is faster than airflow B, a lifting force results, following Bernoulli's law. Raising the corrective lever, the aircraft starts to rise up when the lifting force is greater than the weight of the craft. When the aircraft leaves the ground, the helicopter starts to rotate in the opposite direction to the main rotor rotation. This is the result of the opposing force that is generated by the engine as it turns the rotor. This is known as torque. This means that an anti-torque system is needed to counteract this torque. In the case of helicopters with a single rotor, the tail rotor is set to do this. This is controlled by the anti-torque pedal. If you pull the corrective lever in order to achieve lift, the resistance applied to the blades increases and rotor speed of rotation falls. Most helicopters have mechanisms that automatically adjust engine output so that constant rotor speed can be maintained. As a result, as engine output automatically increases to make up for the drop in rotation speed, torque also increases. In other words, to achieve greater lift, the anti-torque force applied must be greater. In hovering mode, if the cyclic lever is inclined forwards, the lifting force at the front of the main rotors decreases, whilst lifting force at the rear increases. By varying the lifting force at front and back, the main rotor rotating surface inclines forwards, and as a result, the thrust of the main rotor that is facing directly upwards tilts forwards, generating a propulsion force. So the craft starts to move in the direction in which the cyclic lever is pushed. The aircraft starts to move forward as a result of these actions, but at that time the lifting force decreases in proportion to the force diverted to propulsion, momentarily dropping. Hence it is necessary to pull slightly on the corrective lever and supplement any shortfall in the lift force. Once up to a certain speed, the airflow through the main rotor increases, and lift generating efficiency starts to increase. This is called forward lift, and it is possible to move forward maintaining altitude. With strong side winds and as speed of travel increases, the nose of the aircraft naturally tends to turn into the wind. This is because, as with weather vanes, the tail blade at the rear of the craft provides resistance, turning the aircraft into the wind. This is known as wind effect. When flying fast, this wind effect is used in making turns. When you want to turn to the right, lean the cyclic lever to the right, inclining the rotor rotating surface to the right and making the aircraft move sideways. By changing the way the main rotor faces, the propulsion force is in a diagonal forward direction, and the relative wind direction changes too. So, with the wind effect, the nose of the aircraft starts to turn into the direction of travel. As a result, the aircraft turns whilst banking. As lift again decreases, you either have to correct upward slightly or move the cyclic lever back towards you a bit until the torque and anti-torque are in balance. Hovering makes air rescue activities possible and is perhaps the quintessential characteristic of helicopter operation. To do this, lift must match aircraft load, and torque and anti-torque must balance. Whilst hovering, altitude adjustment is done using the corrective lever, and to change the direction the aircraft is pointing, turn using the anti-torque pedal. Use the cyclic lever when the aircraft is traveling horizontally. Also, when hovering, whenever the aircraft is close to the ground, lift efficiency increases. This is known as the ground effect. This effect occurs when the altitude is equal to or less than the diameter of the main rotor. It happens at very slow speeds and where the ground is flat and firm.